Alright, let's look at problem number 2, multiplying and dividing functions. Let f of x equal x squared minus 9 and g of x equal x plus 3. What are f dot g and f divided by g in their domains? Well, we're going to go ahead and rewrite f times g of x as f of x times g of x. And we can substitute the values we have, x squared minus 9 and x plus 3 right here. Using our distribution, we can multiply the first one, x squared times x, then x squared times 3. Then we're going to multiply negative 9 times x and negative 9 times 3. We'll get these four terms. Now, it tells us to write it in standard form, so we're going to put them in descending order. This is an exponent of 3, then an exponent of 2, then an exponent of 1, and an exponent of 0. Putting those all together, we have it now in standard form. Let's find f divided by g of x. And what we're going to do is go ahead and rewrite the top and rewrite the bottom, x squared minus 9 divided by x plus 3. And since we don't see anything the same, we're going to go ahead and factor the top. So we have x minus 3 parentheses and x plus 3. How do we get that? Well, we know that x squared minus 9 is the difference of squares. X times x makes x squared, and 3 times 3 makes 9. In this special case, when there is a minus sign in between them, we can write it as x minus 3 and x plus 3. Notice the parentheses show us our groupings, and that x plus 3 divides by x plus 3, so it cancels out. At the very end, we also need to put this little part here where it says x is not equal to negative 3. Because remember the denominator? That part cannot be equal to 0. So what number makes x plus 3 equal to 0? That's the number negative 3. Alright, so we know that in both of these cases, we can find the domain by looking at what is the domain of f and the domain of g. The domain of both f and g is a set of real numbers, so f times g is a set of all real numbers. However, the domain of f of g is all real numbers except for x equal to negative 3, because g of negative 3 is going to equal 0, and we don't want a 0 in the denominator. So if you've got it, go ahead and work out these problems, and we'll get back to you. After this, go ahead and pause the video, and then we'll work on problem 3. Alright, the next topic we're going to be talking about is composition of functions. So here's a diagram of composition of function, and that is when we're taking an input, and after we put that input into some kind of machine, we get an output. That output becomes the input for another machine, and then we get a final output. So what is this like? This is like when I am baking a cake. I'm going to go ahead and put in all my ingredients, my eggs, my flour, my sugar, baking powder, and other items into my bowl. And those are my inputs. I've mixed them all together, and now I have this really nice batter. But it's still not a cake yet. So I have to take the batter in a baking pan, and then I'm going to put it into the oven. And when it's done in the oven, it's going to come out a cake. So do you see that process where I've taken my batter, that's the result of all my ingredients, and then I take that batter and I've got to put it into the oven. Okay, so then we're going to look at two functions, and again these two functions form a composition function or composite function. Our notation for a composite function is a little bit different. It looks almost like a multiplication, but notice that the circle is open and is defined as g of f of x is g of f of x. Notice the way I say that f of x indicates that f is going to get evaluated first. I consider this like the onion rule. I'm going to start on my inside and might work my way out. So whatever is closest to the x is the first part that's going to get worked, and then the second part is the g, which comes on the outside. Whatever the result of f goes into g, and then I'll work out g. Now notice that function composition is not always commutative. That means if you switch the order, you're not always going to get the same result. So order matters when you're composing functions. Alright, we're going to go ahead and look at two methods of composing functions. The first method is where we're going to go ahead and simplify by finding a rule, and then we're going to evaluate. So let's look at this first method. In order to simplify it, we know that we have a combined function of g of f of x. So what goes in the inside of g? Let's go ahead and look at f. F is x minus 5. X minus 5 is going to go inside of the g function. All right, so x minus 5 is now my output of the f function, and it's going to go inside the g function. So you look at this g function and see where that x is. It's like I'm putting a box right there where that x is. And I'm going to put the x minus 5 right into that box. Notice how this works out? I've got x minus 5 squared. All right, now that we've finished out our function, our composition function, we're going to take negative 3 and input it. So negative 3 is now going to go where the x is. Negative 3 minus 5 is negative 8. Negative 8 squared is 64. That's method 1. Method 2, we're going to go ahead and evaluate directly. That means we're going to take this negative 3 and see what happens when we get the f function as a negative 3 with a negative 3 input. So negative 3 minus 5, using the f function, which is x minus 5, we get negative 8. All right, that's our new output, and then we're going to input that into the g function. So negative 8 squared, according to the function, we're going to put it where the x is. Again, you put that little box. Negative 8 squared will give you 64. Notice that you get the same answer 2 different ways. So if you got it, go ahead and try out that problem. And we'll see you back with problem 4. All right, problem 4 is just like we talked about with the sofa problem, but this is dealing with pizza. You've got a coupon good for $5 off the price of a large pizza. You also get a 10% discount on any pizza if you show your student ID. How much more would you pay for a large pizza if the cashier applies the coupon first? So, we know that the cashier applying the coupon first is going to be more money, so let's go and work that out first. Step 1. Find functions c and d that model the cost of a large pizza. Let x equal the price of a large pizza. Let the cost using a coupon be x minus 5. Notice that we're just taking $5 away. Let the cost using the 10% discount be x minus 0.1x. Remember, 0.1 is the same as 10%, and we're left with 90%, which is 0.9x. All right, step 2, compose the functions that apply the discount and then the coupon. So if we're going to write this out in notation, coupon is last, discount is first, so discount's going to be closest to x. So this will be 0.9x, and then we'll apply the coupon, which is subtract $5. If we do it the other way and apply the coupon first and then the discount, the c is the closest to x, so it's d, then c, then x in our notation, and c of x is going to be x minus 5, and then we're going to take that and put it right here in this box, and we're going to multiply that by 0.9. We can distribute right here because there's no exponent, and we get 0.9x minus 4.5. All right, subtract the composite functions to find out how much more you would pay if the cashier applies the coupon first. So notice the c is next to the x, so that means coupon was first. 0.9x minus 4.5. And second part is coupon's last, so 0.9x minus 5. Remember with that subtraction, you're going to distribute it, so you switch the signs. You have 0.9x minus 0.9x, and negative 4.5 minus 5, which they have rewritten as plus 5, and we find we have 0.5. So remember 0.5 indicates dollars, and you pay 0.50 dollars or 50 cents more if the cashier applies the coupon first. All right, if you've got it, there's a problem right here about a store offering a 15% discount on all items, and employees get a 20% discount, employee discount. Write the composite functions and work it out. All right, we've looked at a lot today. We've looked at multiplying and dividing. We've also looked at composition functions. So what's our focus question? How are function operations different from operations on real numbers? And the answer is the function operations of addition, subtraction, and multiplication and division are only defined for values of x that are in the domain of both functions. For the composite function, g of f of x equals g of f of x, the domain only includes those values of x for which f of x is in the domain of g. All right, we've covered a lot today, and hope that you learned a lot about these function operations, and I'll see you in a class.